Phase distortion synthesis and me have a long history that goes back to my early days trying to write synthesizers. One thing that always appealed to me about phase distortion is that it could make analog-like sounds without all that complicated filter math. Now, it's not quite the same thing, not quite the same sound, but it was enough that it had me intrigued. So when I first started playing around with DSP code, I wrote what I thought was a approximation of phase distortion, and actually was nothing like it, but I didn't know that at the time. But I kept researching it, and when I got to college, I took a couple sound synthesis classes, and one of my final projects was a phase distortion synthesizer. Now, again, lack of expertise kind of bit me because I was only able to get these sort of resonance waves working. I wasn't able to get the main waveforms going without knocking them out of key, out of tune. And I'll talk about why that is later in the video. Later on, I got kind of re-obsessed with this form of synthesis, and my first VST that I wrote, my first software synthesizer that I released, was Digits, which was based upon this technique, but I wanted to take it a bit further than Casio did. And by the way, that's what you're listening to right now in the background, is a song made entirely with the synthesizer technique. And the synthesizer that you're looking at right now is the CZ1000, which I believe was the second such synthesizer to use this technology. And aside from it being the inspiration for my very own synthesizer and a sound that I really love, I also still play this very same keyboard in concert, and here's a photo of that right here. Okay, just to give you a taste of what this synth can do. Now let's take a look at the raw waveforms that the synth produces, and the whole filtery sound of this is just the oscillator, and these are the basic building blocks of a phase distortion synthesizer system. Okay, so let's see how these waves can be created by altering how we read through this cosine wave. And we're going to use the saw wave as an example because I think it's the most basic. This distorts a cosine. Some of the other ones they use, I believe, sine waves to distort, and we can look into those later. And this is going to require some algebra. And so if you remember from high school, or if you're like me, college, because I was late, that's why I went to this place, because it was the inaugural year and they let me in to the comp sci program before I had calculus as a prereq. So that was awesome. Anyway, we're going to use y equals mx plus b. And if you remember this describes a line equation where this is going to be slope, which kind of adjusts the tilt of your line. So if it's just 1, giving you y equals x, it's 45 degrees. For every time you go to the right one, you go up by 1, right? And as you adjust it, you get different slopes. And you have this y offset. So after you've adjusted your slope, you're going to use the y offset to determine how much you want to raise or lower it. So if you remember from the oscillator design segment, if you've got a y equals x read, that's your 45-degree line, you're just reading the waveform. But if you start bending this is where things start getting interesting. So if you read the first part fast, the second part slow, and you keep doing this, you'll get that kind of saw wave, because it's gonna produce something like that, right? First part of the cosine is read fast. The second part read slow. Okay, so how do we accomplish this? Let's draw some axes here. And we're going to use two different line equations to determine our read speed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And here's our 45, let's say here's our 45-degree line. I can't draw to save my life, so let's try to line this up here. Is that right? I don't think this is right. Whatever, we're gonna wing this. We're winging it. So we'll draw a dotted line. That's your 45-degree. Y equals x. Slope is 1. B is 0. Yeah, whatever. That's pretty off. So we're gonna say that this is 1.0. That somewhere around here is 0.5. Okay. And what we're gonna do is we've got this sort of this node here halfway through, and we're gonna cock this back some arbitrary amount. And the more you cock it back, the sharper it gets, the more it changes from that cosine wave into that saw shape. So let's say we put it back here. We're gonna have two lines now that meet at this 0.5 at y equals 0.5. And I like using old school school supplies. They're just fun. I like writing stuff out, like the physical touch. And this has to ramp then from 0.5 to 1.0, right? And this is going to extend this other way, because these are not line segments. These are full-on lines. We decide where they begin and end. Okay, and it's going to extend all the way down to the axis here. So we've got two different line equations, and which one you use depends on whether we're before or after this midpoint, this 0.5, y equals 0.5 point. So the first equation is just going to be the first slope, y, m1, times x, plus 0. And we're going to scratch this out because plus 0 is the same thing, right? So we really just are concerned with one multiplication here. The other equation, the less steep one, is going to be m2x plus b2. So now we got to find what m1 is, we've got to find what m2 is, and we've got to find what b2 is. And you can basically just find m1 and then derive the rest. So if you remember this, what slope is, it's how much, it's rise over run, right? It's how much you're going upwards versus how much you're going the other way. So the reason you get 45 degrees when it's 1 is because for every time you go up 1, you go to the right one. one right one. But let's say this is cocked back to, you know, 0.1, right? 0.1 comma 0.5 is this node. Let's just pretend. I don't know what I actually drew, doesn't matter. So that means that by the time you're 0.1 through this waveform, this wavelength, you've already hit the midpoint. So what is that? What slope do we need to do that? So we're going to say that that M1, actually where's filled out here? M1, I keep writing I instead of 1. It's going to be, the rise over run is going to be 0.5 always, you're halfway through, divide by 0.1. And that'll give you the right slope. Easy, that's the definition of rise over run. What's M2? Because you got to finish up the rest in the same time, right? How do you go for, you know, this is again, of course, another 0.5 gets you to 1. How do you get from your 0.1 into this waveform and you have 0.9 to go? How do you figure out what that is? Well, that's 1.0 minus 0.1, because that's what you got to get to. Same 0.5, because this is 0.5, we're going another half up. And there you go. So those are your two slopes. Now you got to find B, and B is easy. It is 1 minus that, I gotta look it up. I said it's easy. Yeah, okay. It's, well, that was an interesting detour. It's 1 minus M2, right? So now we have the three equations that we need to put this into action. And, you know, we can stop using, you know, I like using concrete numbers when I'm figuring this stuff out, and then you know, replace it with variables. So we'll see that in action when we look at some source code. Okay, so here we have the source code that I typed in earlier today. And, you know, as usual, this isn't the best form for programming. It's more just tutorial style. And as we go along, I'll show you a few things that I would have done a bit differently. So, you know, I got my render function. We're going to be passing in a floating point array that we're going to fill. We've got how many samples we want. We've got what pitch we want in terms of the frequency over the sampling rate divided by the sampling rate. And if that's really mysterious to you, you should go and check out my video on building basic oscillators. And then we have X1. And what X1 is how much we're cocking back that node that we talked about earlier. Okay. So we have the position that we're reading through from 0 to 1, you know, and that's kind of like the linear reads in our traditional oscillators from before. Again, check out that video if you haven't yet. And we have the warp position. That's what we're going to return after we do that math to figure out where we really are on that cosine, what we want to return, what we want to fill the buffer with. And then we have our two slopes, M1 and M2. And then we have our y offset for the second equation. Okay, so we're just going to calculate all these just for clarity at the top. So like I said when I was doing the math on paper, this is 0.5 halfway up divided by how much we're cocking back that node. The other one is, and we're going up another half divided by 1 minus the, you know, how much we're cocking the node back. And then we've got for the y offset 1 minus M2. Okay, great. So this matches up with all the math that we already went through. And, you know, feel free to rewind and rewatch parts of this, and it's just all part of the absorbing the material, really. So as we go from 0 to 1, our oscillator goes from 0 to 1 and back and loops and whatever. We have this what's, you know, called a piecewise equation, right? So if it's below this node, if you're below it on the x-axis, we want one equation. If we're above it, we want the other. And one thing to be aware of is that this does introduce a knee, a sharp corner, in your wave. And if you watch the bit on aliasing, you'll know that that can be trouble. But we'll get to that later. For right now, we want to return one slope times a position if we're on the faster part of the wave, and if we're on the slower part, we return this other equation plus that offset, right? Okay, so that matches up with perfectly what we had on paper. So we're going to fill the buffer with this 2 times pi times the position, but we're going to use this warped position, the position that we're looking up on that graph. And the reason we do it like this, so when I did my exercise for college, what I tried to do is I had 2 different speeds, and depending on whether you're in one half or the other, I would increment by a different speed. And that sounds very similar to this, but it's not, because that one sample that you're missing as you kind of go over that threshold is enough to throw the pitch off as the node kind of is pulled back and forth. And if you don't understand that, that's okay. You can try that out and see what you get. It's interesting. But yeah, this is the way I recommend doing it. And this actually ended up being very fast. When I ported my synth to mobile devices, I ended up not really having to optimize this part. Now, Digits, my synthesizer, doesn't do this for every sample. It actually does it for, let's say, every 30-second sample or something like that. So it kind of has its own internal frame rate. And another thing, too, is you don't have to calculate M1, M2, and B2 every time, because over here you're only using M1. And over here, you're only using M2 and B2, so you could actually move these to where they're needed. There's also the matter of you could do this in a more vectorized form, and I could talk about that if anyone's interested. I'm not totally sure if that's faster, but you would get rid of this conditional here. But that's more of a programming topic than a DSP topic per se. Well, it's literally a DSP topic because it's uses DSP style functions, but it's not about the actual synthesis, it's about optimization. Anyway, I'm kind of rambling here, so I'm hoping I'm not throwing you off too much. Essentially what we're doing is we're taking what we drew on paper and we're making it into this program. So let's see what this outputs. Okay, so I've loaded our waveform up that we've produced using the program that we just wrote. And you can see, here's our saw wave. And you can see from here to here, it's being played very fast. This is your cosine, so it starts at 1 and drops down to -1. And then it's going to rise slowly over here. So this is kind of the cocked back part, and it rises over that node, and then it slows back down. And what I was talking about with tuning, is you want each of these wave cycles to be the same length, no matter how sharp or sine-like your sound is. And using a table like that, an actual piecewise equation, is a great way to keep it all in sync with itself. So let's listen to kind of what we have here. Okay, well, it's pretty boring. It's not super saw-like because the node wasn't back all the way. And you can make it more or less saw-like. Like the Casio that I was showing you earlier, it fades into a nice pure sinusoid, and when it's back all the way, it's like almost like a pure saw. So this is a very useful building block. And you might be wondering, okay, what about all the other wave shapes? What about square? What about the pulse wave, the sine pulse, and all that stuff? Let's cover that next time. And in the meantime, ask yourself some questions. What happens if we run this wave shaper that we built twice per cycle? So for run it once for one half and once for the other half instead of running it once for the entire wave. What happens if we put a sine wave through it instead of a cosine wave? And that'll get you some more wave shapes. And I'll talk more about what I did when I wrote Digits. I added some extensions. And I want to talk about one thing too, is that if you feed it, let's say, another waveform, like a rich waveform, like a square wave, and you apply this wave shaper, what you get is different square wave widths, because it's squeezing the first part of the wave and it's elongating the second part, which is exactly what you want when you want to modify the pulse width of a waveform. In some synthesizers that's called symmetry. So this is a multi-use wave shaper. It's not just if you want nostalgic Casio CZ phase distortion sounds. It can actually do a lot of other things. It's a pretty cool technique, and we're going to get deeper into it next time. So thanks for tuning in, and if you got any questions, please write them below. If you want to see me cover something in particular, write it below, and I'll hopefully have another video up before too long. Thanks for watching.